Welcome to this update on ARC AGI 2, where I'll be talking about team progress and also some thoughts on how we might solve this challenge. Now, I'll start off with the main news here, which is that myself and Lewis Hammonds have decided to form a team. And I actually have Lewis here on this video. So I'd like to just introduce Lewis and maybe let him say a few words about himself. Go ahead there, Lewis.
Hi. All right. Yeah. So very happy to be working with Ronan. I think we've both been very drawn towards ARC as a important problem for AI for quite a while. I recently left my job at Google and previous startup experience to work on this full time. And I've been writing a bit about ARC, doing recent review of the literature, and then also some more recent thoughts in collaboration with Ronan on how we want to approach this. So yeah, excited to get stuck in, excited to build out a team, get more people in the UK, in Ireland, in Europe, or the world, really talking about how we solve this and collaborating together.
Yeah, great. I suppose we should say, Lewis, maybe those who've watched the channel before are familiar and those who've read your blog, but ARC AGI is a challenge that is somewhat feasible for humans, but difficult for these large language models or other approaches. And they involve solving these grid patterns where you have to transform from a set of inputs to outputs. You have to detect the transformation and then apply it to a new grid. And we'll be talking about some of the approaches towards it today. If you are not too familiar, there is some recommended reading here or watching. There's a video on the Trellis channel, which I've linked here in the slides. I'll put a link to the slides in the description. And over on Lewis' blog, which is quite comprehensive, there's a new post that went up yesterday on how we think one might approach beating ARC AGI 2, which is the competition that's up for this year. And there are quite a few other blogs that I think are relevant, particularly Lewis' overview of the 2024 solutions. Lewis, anything you want to add there, or maybe direct people to certain content on your blog page?
Yeah, no, I think we'll go through a lot of the main ideas. And yeah, if you're brand new to ARC, definitely as maybe starting with the overview is a good place. There's obviously great content on the ARC Prize site as well if you actually want to play with some puzzles and get a feeling for the difficulty and the kind of things in there.
I think that's right. In fact, I usually recommend to people, if they go over to arcprize.org and just click on play here, you can then go and find, start on the hard one, public eval set v2, and you can check out some of the problems here. So you have a transformation going from input to output. In fact, you have 3 different examples, and I won't do it now, but the idea is to try and identify the transformation and correctly apply it to a new test grid here. And yes, these problems are quite difficult for large language models. The problems are designed to be unique and not present in the training data for large language models. And that makes it all the more difficult. Now, before we start, and Lewis and I will give some thoughts on how we might solve this, I just want to mention that we are looking for team members. As Lewis said, they could be Ireland or England, Europe, but you could be based anywhere in the world. And we're looking for potentially 1 to 2 additional team members until the end of July. And if you like, you can learn a bit more by going to trellis.com/arc-agi-2. We're also looking for sponsors who can benefit from callouts on videos like this one and blogs like the one Lewis has written. There'll also be access to sponsor-only webinars where we'll talk with a small group of sponsors, as well as branding opportunities on videos clothing. So if you want to learn more there and get a copy of the sponsor offering, you can also go to trellis.com/arc-agi-2. So I think for this video, we've already done the team update, the apply to join, the sponsor update. We want to talk a bit now on our hypotheses for solving ARC. And we are going to list out how those hypotheses apply to some of the current approaches to solving ARC AGI and finish off then with our research plan. So let me just increase the size of the screen here. Lewis, you can still see that there. Okay, great. So this is going to be somewhat advanced. I think we should give that warning. It's going to include reference to a number of the approaches that are covered in the video I previously made and covered in detail on Lewis' blog. But we do recommend, we have a few papers that we recommend reviewing in advance. IceCuber's original brute force type approach using heuristic search. There's the test time training approach that won the competition last year. It's a neural-based approach. There's the Ryan Greenblatt approach, where he uses LLMs to write Python that then can solve the challenge. That was also from last year, and it's a blog. There's Sebastian Ferre's Object MDL approach, somewhat related to the IceCuber approach, but a more guided way to do search. And then there's also searching latent program space, which is a neural approach involving multiple neural nets, one to encode the input and output grids into a into a latent program, and then one to decode that latent back out into the output that you need from the test grid. So we are going to reference to a few of these and recommend reading them if you want to have a bit more background. So here are the two hypotheses, and we'll lay them out up front and hopefully give more color onto why and what we mean by these. The first is that we believe large program data sets generated through composition of primitives is going to be critical to solving ARC. And the second thing we believe in is test time adaptation. Now, you may be familiar with test time fine-tuning, the winning approach last year, but we would broaden that to cover not just test time fine-tuning with a gradient-based approach, but other types of adaptation, perhaps like getting feedback through recursive calls to an LLM. So we're going to start off with the first of these hypotheses, that large program data sets will be needed, generated via composition of primitives. And there's quite a bit of background that we will need to go through just to explain this. So let's first look at what we mean. We're going to do a few definitions by program descriptions and generation methods. Then we'll talk a bit about primitives and particularly expressive primitives, which we think are critical to solving ARC. And then we'll talk about what training data we need, or we might need, in order to solve ARC. So starting at a simple level, if we look at an ARC challenge, we have an input grid. If we look at an ARC task, we have an input grid. Actually, we have multiple examples of input grids that ultimately need to be transformed to output grids. And to get through that transformation, we typically need to go through generating a program to go from input to output. And then we need to have run that program. So we need to run the program to get a description of the output grid here. Now, the generation itself can be either discrete. So we could do some kind of heuristic search if we have discrete programs like little maybe domain-specific language programs, and we could maybe search through those with brute force. But the program generation could also be neural. So we could have a neural net or a transformer that is going to generate these programs. Now, the program description itself can also be discrete, or it can be neural. So in the discrete case, we could have a Python program. For example, we could have a flip and a rotate of the input to get to the output, but also we could have a description that's neural. So if you look at the test on fine-tuning last year, there is no discrete program description. You can't just write down what the transformation is when you have trained the neural net, but there is an implicit description that is there in neural form. So to apply this to a few of the examples, like IceCuber's approach, which was the winning approach for a few years, you would have an input grid. You would generate through brute force search of C++ programs. You would generate a complete program. You would have a description that is a C++ program, and this would lead then to an output grid. So here the generation is discrete, and the program that you run is also discrete in the IceCuber approach. In the neural net approach, like was done with test time fine-tuning last year, everything is kind of mixed together. So you have the input, you forward pass through a neural net, maybe Llama 3 or a tuned Llama 3, and the neural net generates the program, but the neural net also represents the program. So in a sense, you could say the program and the generation are both neural. In this case here, there is no explicit program description. In the Greenblatt approach, so he took an input grid, inputs and outputs, and will use GPT-4o to generate Python programs. And then he would run those programs. So in this case, the generation of the programs is neural, but the description of the program itself is actually discrete. So you can see we're covering all of the combos. You can have the generation be neural or discrete, and you can have the description itself be neural or discrete. Yet another example here is from Dreamcoder, where a neural net is used to choose some primitives that might be relevant to the ultimate correct program. So here you have a neural net recommending discrete programs, but the program itself is described in a discrete way. So here you've generation as neural or neurally guided is often said about Dreamcoder, and the description is discrete. I think this is the last one here. This is an example of where we've got neural. So you use a neural net to encode the training grids into a latent program. So that describes the transformation from input to output. And then a neural net will be run on that latent program with the test input to generate an output grid. So this is an example of where the generation of the program is neural, but the program itself is captured in a latent, which is also neural as opposed to being discrete in the same way that a Python program would be, or a domain-specific language like in IceCuber. And I should say at this point, we don't have a strong feeling on whether the program generation or the descriptions even should be neural or discrete. Maybe discrete provides more regularization. Maybe there are some smaller arguments or feelings we have there. But I think we do have a strong sense that the training data itself requires discrete program representations, because ultimately this is how you generate data that is more general and it captures the nuance. And that's why it's important for us to describe a bit more now about what we mean by primitives and what it will ultimately mean to vary some of those primitives to get a more comprehensive data set. So yeah, this is the second subpart of our first hypothesis, just talking about primitives and what we mean by expressive primitives. So if you look at a Python program, you could consider a very simple ARC problem where the solution is to rotate first the input and then flip that rotation to give the output. And what we would mean here by a primitive, as an example, would be flip or rotate. So to solve ARC tasks rather, we are looking for a program, which we would describe as this entire thing here, that is composed of primitives, one of which is flip and one of which is rotate. So when we say program, we mean the whole thing. And when we say primitive, we mean a building block, essentially, that goes within that. Now, a few things to know about primitives. If our program is discrete, and we know that program could be neural or discrete, but if it's discrete, we can define a library of primitives. For example, we could come up with a library that contains flip, rotate, map, and many others. Some of the primitives might be overlapping. They might do similar things. We could also combine some primitives to make a new primitive through compounding. Now, the library could be explicit, as I just described, so we can easily describe flip, rotate, map, but it could also be implicit. If you think of a large language model like Llama 3 or Llama 4, it has an embodied knowledge about many, many Python programs. Now, could I write down and enumerate, or could I ask it to enumerate which programs it knows of? Maybe it might be difficult. Maybe you could look at the training data that was used to train Llama and you could get that list. But we would say that there is a library of Python programs here, but that library is implicit. Now, if your program is neural, then the primitives are not going to be clearly defined. You're not going to be able to point to flip or rotate in the same way you would if you were talking about a discrete program. So if you have inputs going through a neural net and then outputs, it's hard to say whether there are discrete primitives within the neural net. Maybe there are, but at least they aren't explicit and easy to describe as they are in a discrete case. So one approach to solving ARC is to have a library that is complete enough, a library of primitives that is. And you'll need at least certain basic primitives. But if you have that library, that's maybe good enough in theory if you had infinite search time. But to be good at ARC, efficiency matters. And so you need to be efficient at finding the combinations of primitives that are going to solve the tasks. And this leads us to a distinction between primitives. Not all primitives are created equal. Some sets are complete, some are not, some are descriptive, some are not. And we'll come to the notion of what we mean by expressive primitives and why these are desirable. And then we'll ultimately get to the question of how we could get to a set of expressive primitives. Now, note that when I talk about completeness, descriptiveness, or expressiveness, this is always going to be relative to a given set of tasks, which ultimately in ARC AGI 2 would be the test set that, of course, we can't see. So I'll talk first about completeness. Actually, you can get a complete set of primitives without having too many primitives. You can have quite a small number. Here, I just asked, I think it was O3 to come up with a list of a 12 primitive core. I'm not sure this is entirely rigorous, but the point is, if you have some very fundamental operations, given enough search time and given enough compute, you probably could solve everything. You might even be able to prove that you could solve any particular type of problem. So a small set of primitives can be complete. Now, the problem is if you just naively create a set of complete primitives, but they're very fundamental, you have an extremely large search space. So to get to any possible complete program, it might be very long. It might take you a long time to get there. For example, if you had 13 primitives, the search space might be 13 to the power of 20 here. If you have a program that's going to be of length 20 in order to solve a given program. So just by making the primitives complete is nice in some theoretical sense, but in a practical sense, that's not going to make it easy to solve because we have a very large search space. On the other hand, you could have primitives that are descriptive. So you could have something extremely specific as a primitive, and this is not even that specific, but rotate largest object 90 degrees to bottom right. Imagine just one primitive function that does this. The problem is this will be very descriptive and do well on very specific tasks, but it's not going to generalize. So you can imagine that you would need an extremely large amount of these primitives to be complete because each one is only doing something extremely specific. So what we're really going after is what we're terming here. Maybe there's a better way to term all of this. What we're looking for is a set of expressive primitives. So we want to have a library that's going to be complete, but not slow to search. We want it to be complete and also reasonably easy and fast to search. So we want the primitives to be somewhat descriptive, but also not so descriptive that they won't generalize well across a set of problems that we haven't seen. So this is ultimately our goal. And you can think about it concretely if you look at discrete primitives and discrete programs, but we would argue you can maybe by analogy think of primitives being there for a neural program as well. It's just that the primitives and then the compounding of the primitives is done in some implicit way within the neural net. But as I mentioned already, what we think is key is probably for data generation, you do need explicit primitives, or maybe you do need explicit primitives because you need some way to augment. And we think the augmentation should be in primitive space so that we get good coverage and a data set that's going to generalize well. So this is our first hypothesis, and you can see why I built up to it. We think we need to form expressive primitives during pre-training, probably during pre-training and maybe as well during the task solving itself, which is called test time adaptation. And we also would like to have a program generator that knows how to use those expressive primitives. So we would like the primitive set we're using to be complete. We'd like it to be expressive. And then we need to be able to use those primitives and compound them together when we hit a test time task so that we can adapt and solve it.
So just bringing this back to ARC AGI 2 specifically, one of the things we know about the second competition is that it really focuses on this compositional element where problems require you to do like multiple things in series or maybe in parallel. We can never expect to see all the end-to-end programs that would solve ARC 2, but by having a way to compose these primitives like subprograms, that's going to be an important step and is really highlighted in the ARC 2 problem set.
Yeah, thanks, Lewis. So this brings us to a question of, well, if we want to have expressive primitives and we want to be able to use those expressive primitives effectively, what does the training data look like that we would need to achieve that? And so you can start by thinking about, well, what's a basic way of creating training data? And obviously there are training problems. There's a training set that is provided by the competition, but that data set is quite small. And it contains full end-to-end programs. At least if you solve it to get those programs, you would have end-to-end programs. What it contains is the grids, the inputs, and the outputs. But just looking at this data set, your program generator is not easily going to learn how to create and how to use expressive primitives because it's just been exposed to these either input and output grid examples, of which there are a few, or if you manage to solve them with an end-to-end program, then your program generator is going to get familiar with that end-to-end program, but not necessarily with little tweaks around the primitives within that longer program here. So perhaps it's better to ask instead, where do the ARC training tasks come from? And ultimately, these tasks come from humans, as we understand, who are using their own some set of primitives, the ARC team, to create and solve problems. Maybe they have an idea to pattern out a snake, create a pattern along kind of a snake type path, and they want to make every second one a different color, or maybe they have a shift and rotate. So these are some ideas that the humans in the ARC team are coming up with, and they're combining them to create these complex problems. And you might think of these primitives, and I'm not saying we could delineate exactly what they are in Python form, say. These primitives are what might be referred to as the ARC core knowledge, and you'd hear this talked about in the ARC competition from time to time. So what we're saying is we need a way to start with a training set, but then extract some expressive primitives and combine those expressive primitives to create new training problems. So if you think of a long program, we want to identify kind of the building blocks and then vary some of these building blocks to hopefully create a set of training data that teaches the model how to not just write an end-to-end program, but what the effect of varying each piece is. So our thought here, and I admit, we will admit this is quite general. We don't have a specific recommendation because we've yet to try a lot of things out. But the idea would be to start with a training set, find solutions, program representations. And to make it concrete, you could think of finding Python programs that will solve a given task, decompose that into expressive primitives, and then recombine those primitives in different ways. I'll talk about some ways you might do this, but recombine some of those primitives in a way that might be similar to the full program, but a little different, and try to teach the model how those little variances in primitives will affect the overall program. And I won't dwell on this too much, but in principle, you could think about taking out primitives, randomly combining them. Maybe that gives you overall programs that are not quite representative, so not that useful. You could, of course, try to brute force cover all of the space, given all the primitives you've extracted. That's going to be too many permutations. So there's the question of, well, how can we do better? How can we take some problems, decompose them, and then vary little pieces in a way that's more systematic and more aligned with the type of task and the type of human primitives that are being used to generate the problems in the first place. So here's a little representation of how that might work. You have a seed program that has 4 primitives, and maybe we would swap the third primitive for some different primitives so that we teach the model not just to be good at this entire program, but rather to be good when we vary one small aspect. So yeah, I'm just illustrating here, if you do this brute force by doing all of the possible combinations, that's going to be, it's going to be unwieldy. So perhaps by just swapping one at a time or finding ways to smartly make swaps and vary the program as a whole via primitives, you're able to reduce that space down, but make it more targeted towards the types of problems that we see in ARC. And so this was kind of quite a few slides to explain our basic hypothesis here, is that we think decomposition is critical for generating a training set, decomposition and then smartly tweaking these primitives along the way to give us a rich data set that's representative of the ARC domain. Now, the second thought here, the second hypothesis we have, it may be a bit more succinct to describe, is around that of test time adaptation. And you may be familiar with this approach from last year's competition, because this was a key approach in the neural, the architect's winning approach involved using a neural net to predict grids directly, no Python programs, just directly predicting grids, but they would then back propagate on the training examples with one withheld, and that back propagation on the test time samples, that would allow them to improve their performance quite significantly, actually. So we think that this ability to adapt when you see the problems is quite important, but we also think that the back propagation that was used by architects is not the only way you could do this. So we see a few ways of doing test time adaptation, and we think possibly this is critical as well to performing well. So I'll make an attempt here at describing test time adaptation in a broad sense, I think Lewis and I sometimes have different definitions or ways of describing how this works, which is fine. Some of these concepts we're still wrapping our heads around. But broadly speaking, each ARC task consists of some training examples where you have an input going to a training output, and then some test input that you need to apply a transformation to and get the target output here, which hopefully is correct. Now, what test time adaptation involves specifically is taking the inputs, generating a program and running the program. Maybe this is all one step if it's a neural net, and getting the outputs. Or maybe it's 2 steps if you generate a Python program and then run the program, for example. Then you would compare the predicted versus the actual train outputs and somehow provide feedback to the program generator here. And once you've provided feedback, you will then take the test input, apply the updated generator, and hopefully get to the right test output. And the way you give that feedback can depend. If this is all a neural net generating and running the program, then you would backpropagate. But if it's, say, Python code being generated by an LLM, and then you're running that code, maybe you would just send back feedback directly in text form to the LLM and have it adapt in that kind of a feedback manner. And yeah, I've just, I think, said already what's on this slide. If it's a neural net, you can do backpropagation. But if it's, sorry, my slides are jumping around on me here. But if it's an LLM, then you can call the LLM again with feedback. So you'll have your training input output, your test input, the result of running the first program. This is the first time around. But then you'll go back to the LLM, and given the result of the first go around, you'll say, please generate a better program. Now, there is a small comment here, which I won't dwell on. Technically, in Dreamcoder, there is an approach where at test time you could, this is, I think, not done in the original Dreamcoder paper, but in principle at test time, you could see if there are some primitives that can be compounded or combined in order to do what did take maybe 3 or 4 steps in one step. So there's also this idea of compounding primitives that is relevant if you're doing a neural search through primitives. It's a bit of a side note here, but in principle, this might be a form of test time feedback that is also possible. Now, why do we like test time feedback? Theoretically, it allows us to be adaptive. Hopefully it would allow us, as Lewis interjected there, to do something compositional when we get to test time. And in practice, we have some empirical evidence because it definitely helped the architects with a neural program approach in 2024. And also Ryan Greenblatt, when he, don't know why I capitalized the B, when he ran his approach last year, he ablated and he found that doing this layer of feedback also helped. And we've seen that in some other papers as well, that running feedback, perhaps particularly with fine tuning and perhaps particularly after you've already done sampling, so you've got the breadth of good examples and then you feedback, this can lead to improvements. And so we've got some empirical basis for why feedback here might make sense. And this kind of rounds up, I think, our 2 hypotheses here. The first is on generating programs generating data sets rather via composition of primitives. And the second is around the importance of test time adaptation. I'm not saying that our thought here is new, but the way we like to think about it maybe is a bit broader in terms of the forms of adaptation that we would encompass. And we're coming to the end here, but in terms of research plan, I mentioned before, we're somewhat agnostic to the specifics of the approach. We're trying to get familiar with all, whether it's neural discrete, whether it's a purely discrete approach. But we do want to follow these 2 hypotheses here. And that probably means building a data set where we have primitives we can point to. And so one task we have on the roadmap is building a data set of Python solutions to difficult ARC problems and thinking about ways we can augment those problems at the primitive level to expand and generalize the data set. Then with those programs in hand, we can actually look at a number of overall approaches, whether they be generating Python programs or whether they be using neural nets as in the searching latent space approach. So somewhat agnostic here on the ultimate approach, but feeling like the direction of having these data sets where we can augment on a primitive level makes sense, and feeling like incorporating the adaptation makes sense too. So yeah, if you are interested in joining Lewis and myself, you can visit this website here where you can drop us an email And if you're interested in sponsoring the team, we are also keen to hear from you. The same website, you'll find a link there you can use just to, rather an email there where you can reach out to us. And I think, Lewis, unless you have anything else you want to add, that brings us to the end here.
Yeah, that's all great.
Okay, great. And let us know in the comments if you have any questions or comments. And we'll be sure to get back to you on those in the comments below. And looking forward to the next update. Cheers, folks.